Hello, operating systems people. This is Gabriel Palmer, and today we're going to talk about file system APIs. See where that goes. Okay, so we know that operating systems are about many things, but one of the dominant things, one of the most important things, is they're about abstraction, right? One, deal with the hardware below, figure out how to multiplex it. Two, provide abstractions to user level to do useful things. Operating systems are there to make applications useful. So, how do we do that for file systems? What is the abstraction for a file system, right? So we want it to make the system easier to use. We want it to take a lot of the esoteric details of what's happening underneath, what's happening on the raw system in the hardware, and abstract that away. We've seen that for scheduling and for memory, where scheduling provides the illusion of exclusive execution. Threads do the same. Virtual memory provides the illusion of exclusive memory access. You don't need to know about the other things that are running on the system for either of these systems. So the operating system hides that fact. You get to program your programs such that they think they're the only program. Now, what would an abstraction for other devices look like? Disks, terminals, keyboards, interacting with other processes. We've seen a version of that with send to and receive from, right? Or send message and receive message. So what does it look for like for devices, for disks, for solid state disks, etc.? Note, today I am going to be using the term disk, and that's generic for like spinning medium, solid state devices, etc. It's hard often to figure out what you actually want to target when you're creating an API. What do you want to make the API do? What are you optimizing for? There are a lot of conflicting opinions about this. There's one that I think is fairly universal, and that's simplicity, right? KISS stands for Keep It Simple Stupid. I think it's pretty universal. You always want an API to be as simple as possible, but not too simple, right? So some examples of kind of the size of different APIs here, and you can read into this as much as you want, but it's a surface level thing. The original Unix that we're all using with XV6, it was between 10 system calls, and it kind of beefed up to 60. Linux, on the other hand, has hundreds, upwards of 350 system calls at this point, and keeps accreting them over time. And we have Windows that is in the multiple thousands of system calls, largely because of the development process and how it's structured. So as you get more APIs, just full stop, things get more complicated. It would be much better if you could fit everything that you need in a system into a smaller number of easy-to-use system calls. Of course, this is a holy grail. It's easy to say that, hard to actually do it. Okay, so we're going to be talking today about the abstraction that we have in operating systems for a disk. And again, by disk, I mean solid state disk, whatever. At its core, a disk is just a large array of bits, just like physical memory, right? It's partitioned into sectors. Usually these are 512 bytes, but most operating systems just treat these as basically frames. So think of them as 4096 chunks of memory that are 4096 aligned. These are kind of the unit of transfer to and from a disk. So when we think about using direct memory access, DMA, and asking the disk to do a transfer, we're typically asking it for a number of sectors to transfer into memory. So our DMA ring is configured to transfer multiple sectors in for each of these types of requests. And most importantly, of course, the disk is non-volatile, right? This is its big discriminating factor from memory, that when we remove power, the data persists. It sticks around so that we can reboot and we still have access to the data. And memory is volatile. When we remove the power, it's gone. There's really exciting technology around the corner where we can actually have non-volatile memory. But we aren't quite there yet. Hopefully I'll have some time to talk about that later. Forces some very extreme decisions in the design of operating systems. Okay, so the big question is, how do we share the disk between many processes, many users, many competing principals that want to use resources within the system? And of course, one of the primary things that we need to focus on is protection and security within the system. So basically, how do we then make it easy to use, right? How do we protect what we need to protect and multiplex that hardware resource amongst multiple principles? And then how do we make it as easy to use as possible? And then, of course, how do we make it as fast as possible? Often these things are in opposition. If it's really, really easy to use, maybe it's really hard to use. Okay, so you all probably already have some notion of what the answer to this is. The answer for trying to provide an abstraction for the disk often starts with files. These are logical storage units, and they're just collections of related data. And we think of them as being contiguous, files containing a number of bytes one after the other, just like the disk. But we can have many of them, and each of them only stores related information. Now, the generic storage is basically saying that this data can be almost anything. It can be just an untyped sequence of bytes. So it can be binaries, it can be ASCII, it can be structured documents, XML, HTML, it can actually be databases, right? All of this can be stored into a file simply because it is an untyped sequence of bytes. Now, this might raise a few questions. It raises a question of, should we actually have more structure? We like structure, we like our data to be easy to digest, so it would be really nice if we could do so here. So it kind of raises the question, why not store everything as HTML? Microsoft was looking at some of these ideas in the mid 2000s, and they all kind of fell flat. And we're kind of stuck with these files that are just unstructured text. And it tends to work out generally well because we have a generic abstraction that can be used for many different purposes, right? Now, files alone are not quite enough, so we also want directories. And directories are simply the idea that, you know, we have some sort of a containing abstraction that denotes a group of other abstractions, right? So the directory contains a group of files, presumably those files having some sort of relationship to each other, right? Now, files conceptually include a name, which is a human usable identifier, an identifier, which is an ID, which is usually an inode number, which we'll figure out what that is a little bit later. This is just a unique ID for now. A size, a date, a time. There are multiple times associated with each file: when it was created, when it was accessed, when it was modified, etc. And a number of pieces of metadata for protection. These includes things like which user the file belongs to, which group it belongs to, whether the user file and other people should have read, write, execute, etc., etc., etc. Windows includes much more descriptive access rights and extensions to Linux, whereby we are able to put different read, write, executable permissions for different groups of people and different specific users in a much more expressive way. So we don't actually want just a collection of bytes associated with a file. We also want all of these different things as well, right? Now, there's a question about how we name things in a system, and naming is actually one of the fundamental things that systems do, not just operating systems, but systems. And the reason for this is because systems typically coordinate resources. These resources could be disks, could be memory, could be threads, could be servers, could be data centers. And because systems are concerned with resources, systems are concerned with naming those resources. Naming is the way that we refer to those resources. So, for instance, on Discord, you know what my name is, right? You know my email and the way to reach me. You know my YouTube channel and kind of my identifier, which is a unique identifier associated with my user ID. All of these highlighted in purple here, right? But of course, those are kind of, the abstractions built up by multiple layers of abstraction for web applications in one way or the other. On a current system that we're talking about, in a single system with operating systems, we think about resources in terms of memory, threads, processes, etc. So we know that when we're executing in a process, we can form a pointer. That pointer has an address to a piece of memory in the virtual address space. That virtual address space is the namespace for memory that a process has access to, right? We've seen that when we call fork, we get a process ID back. That's within a PID namespace, etc., right? These are the names that we choose to assign with some sort of resource. And we often actually think of them formed in hierarchy. So these are kind of concentric enclosing concepts. So emails are actually a decent idea, or a decent example of this. We have kind of the EDU namespace, which is all of the educational units. We have GWU, which is, of course, George Washington. We have email versus GW mail, which I still have no idea what it is. And then we have the username associated with that, right? And then for each of our classes, we have within GW, there being the C School, School of Engineering and Applied Sciences, we have Computer Science, and we have this class 3411, right? So you can see that we have these concentric kind of circles of different concepts. And we organize these using directories in file systems, right? So we have our directory namespace, which allows us to define groups of files that are logically identified with each other that allow us to both sort them and associate some sort of locality with them. The operating system might find it useful to be able to access, if it accesses one file in a directory, be able to access others relatively easily. So this is useful for both operating systems and for users. One way to think about these namespaces is a single level directory. So if you think of like my GitHub account, I have all of my repos, the things like FOS that we talked about, lock-free, the lock-free in-class exercise, Penny being pausident, the deadlocked one, to go boldly go and find the secret of life and everything. These are all different things in my repo. And that's kind of a single level namespace. I don't have a hierarchy there. Those are my repos. So for a file system, imagine if we had all of your files in your system in a single directory, right? It's not great because you don't have abstraction within that namespace. There's no way to group files together, no locality of access. You cannot necessarily have two files with the same name. I can only have one directory called FOS, or one file called FOS, right? So it is very limiting, very constraining. If you have a download directory that looks like mine, you know the pain of having a single directory where your web browser downloads to by default, right? But there are some upsides to this. One of the upsides is that it can actually be very fast because we only need to optimize a single lookup data structure to be able to make it work relatively well, right? And this is, you see this quite often in web applications. When you go to your Facebook web page, it will look up a number of objects, and all those objects are associated with some key, and you simply get the value back, and that happens to be the thing that you're displaying. So there's a single namespace of all of these keys for all the objects in Facebook. Supercomputers are actually another interesting example of that. How they organize file systems is often with a single flat namespace for all of the file system objects. And then they layer on top of that another system that includes a notion of directories. So if we add directories into the system, we start to see that, yes, we do group files together. And not only does this allow us to group files together, it also allows us to have permissions that map to an entire subset of or an entire subtree of the file system hierarchy. So we can have a directory that has a certain set of permissions on it that might let only some users be able to ascend into that directory. So this can be used generally for access control between different principles within the system between different users. Okay, so let's actually dive into it, right? This is kind of a concept of where we're at. We have a hierarchical namespace. Let's actually dive into what that looks like on Unix. So if we want to use or manipulate this namespace, we're used to doing it at the shell, but when you look into the shell and you look into the programs that the shell is using, it's all just a whole bunch of programs that are using system calls, right? So what are those system calls that they're using to modify and manipulate the hierarchical directory namespace? Well, makedir and roomdir are two of the primary functions. Obviously, this allows you to make a directory and remove a directory. You'll note that a lot of these names match the shell name, the program that we use within our shell, but it's not, that's happenstance, right? Somebody wrote a program that happened to have the same name as the system call, right? So both of these take a path, and they can take an absolute path or a relative path, but they take a path. And this allows us to essentially specify where in the file system hierarchy we want to create this directory. And that the path can have slash in it allows us to essentially have this hierarchy. So that is our interface with a hierarchy, being able to have slash in paths. Somehow, once we go into a directory, we have a directory, we need to have some way to actually figure out what is in that directory, what other directories and what files are in that directory. So readdir allows us to effectively iterate through directory entries within a directory, and we can iterate through and see the names of the enclosed files and directories. Open, you'll notice that it takes a dir ID, not a path, as its argument. Now, dir ID we can get using opendir, and opendir takes a path as an argument. So you can see we kind of are interfacing with that path directory one way or the other. And we kind of need readdir to have this dir ID because we need some sort of an object within the kernel that tracks where we are in our progress of reading through that directory. So we need something to just track essentially the iterator through the for loop, right? Okay, and then rename allows us to take two paths and take the object, the file or directory associated with the first path, and move it into the second path. And there are error conditions if the second path already exists and whatnot. So you can look into those in the man page. Create, there's a great story behind create. One of the creators of Unix was asked what is the one thing they would change in Unix if they could do it all over, and the answer was add an E. They were really shooting for having 5-letter system calls or something, so they got rid of the E, but it's really a create system call, right? So create allows us to create a file at a specified path, and unlink is effectively remove or delete a file. So it's a weird name, and it really proves the point. We did not call the system call rm like we would think just using a shell. It's actually unlink. Now the namespaces here are actually a couple, right? We're using directory IDs for opendir, closeddir, readdir, and we're using our paths that could be absolute or relative depending on whether they start with a slash or not. Okay, so we have this file set, we have this namespace, the paths. Now, how do we actually go through and modify the files, right? Use files, read files, all of that stuff. How do we do stuff with files? So we have a second namespace that's used within Unix as well. And this is that we have per process file descriptors. So file descriptors are the first arguments to each of these functions. And whenever you see that within a C API, you could almost think that it's often an object-oriented API, where you might think FD is instead the object. So you could almost think of these as being like fd.read, but we're using C, so it's the first argument. This is a common way to write C APIs. So if we call read with file descriptor, we're trying to retrieve the contents of a file sequentially, one byte after the other. Write, we want to write bytes from an array in our memory into the file, one byte after the other sequentially. And seek allows us to take a file that we're modifying and actually change where we're accessing within the file. So there's this interesting abstraction of a position in the file. And you see that illustrated in the diagram here. If you think of the file of being of some size, we know where the file starts, we know where the file ends. And as we read through the file, it actually updates the current position so that we don't reread the same bytes. If we ask to read 10 bytes from a file, and we get those 10 bytes, and then we ask to read 10 bytes from a file, it's actually going to read the second 10 bytes from the file. And that's because this current position is being tracked as we read through the file. Okay, so I have the arrow going to the right. As we read or write to the file, it advances the current position towards the end of the file. lseek, the seek API, allows us to effectively change that current position to anywhere within the file. And this is actually amazingly commonly used. This is used in a lot of codecs for like video and audio, and this is mainly used for databases. When a database wants to be able to look up a tuple, look up a record, often there's an index that tells it where that record is. So it might seek within the database file to where that record is so that it can actually read it directly. So this is a relatively common API, but maybe not one of the ones that you would know of. Dupe is a way to duplicate a file descriptor. It's actually very important. It's used by most shells to be able to create new file descriptors in certain locations so that new programs, when they're forked and exec, will be able to access them at specific file descriptor IDs. And close. Close essentially says we don't want the file anymore. Now, file descriptors are nothing magical. They're actually just an integer that's passed down to the kernel in the system call API to do the manipulations on the file. Yeah, okay, so the namespace that we're talking about here is file descriptors, and they're just integers. And they're essentially used to look up in a big logical array within the kernel for each process, which we call a file descriptor table. So you can imagine at a certain file descriptor offset in the file descriptor table, there's a pointer within the kernel to whatever you're using. It may be a file, or it may actually be a pipe. It may be a terminal. We'll see. Okay, so we talked about a hierarchical file system. We talked about file descriptors, and we talked about directory IDs, which I'm going to kind of ignore. So we have these paths in the hierarchical file system, and we have a file descriptor. How do we interact between the two, right? We haven't really got to a point where we can actually like create or open a file and do something with it, right? How do we convert between the two? So we need to interact between these two, and the open system call is one of the main ways to do that. So open allocates a certain file descriptor associated with a certain path in the directory namespace. So it's really important because it takes a path P and converts it into a file descriptor that now references that file that was referred to by P, right? It also is a great time to actually check for permissions to see if you have access to that file. And from then on, we have a file descriptor, so we can access it using all of the normal read, write, close, seek, etc. Now this kind of begs a question, right? Like, we have all of these functions that are doing stuff on file descriptors. Why? Right? We should be able to just have read and write that take a path as an argument instead. So I'd like you to actually think about this for a little bit, brainstorm a little bit, and we're going to kind of go through a few reasons. Pause the video, come back. Cool. Okay, so there are a number of reasons, and we're going to go through a few of them. The first major one is that file descriptors are polymorphic. We all know from object-oriented programming that polymorphism is the notion that you can have a reference of a certain supertype, and you don't necessarily need to know what the actual object type is, what subtype it actually is, and the functions that you're calling for things like read, write, and close could be implemented by any number of logical objects, right? Same thing here. We can have a file descriptor, and that file descriptor API, read, write, close, dupe, seek, etc. And we have that nice API that works on file descriptors, and the resource that backs that file descriptor could be defined to be almost anything, right? Unix was actually created around the idea that the file descriptors are amazingly polymorphic and could refer to a very, very large breadth of different resources within the kernel. Different systems like Plan 9, which is let's say Unix++, have really tried to push on this idea even further, right? So you get a very large versatility in a small number of functions. And most importantly, your programs can be written to use those functions, and they should execute identically across multiple different backing resources within the system. So this is really powerful. And you see this here where we have programs that are written specifically for the read-write-close API, and what the resource backing that file descriptor could be a terminal or another device. It could be a file, it could be a networking socket, it could be a pipe, and the program might not even really know, right? So let's go through an example of what that looks like. We've seen pipes being used to string together different Unix processes. So we can cat out a grades.txt file, pipe it into awk, which is just a little program that takes a script and will do something. In this case, it'll print the fourth column or fifth column, I forget, fourth column, I think, of that of the input, and it'll output that file to the terminal. But the terminal actually is piped to sort. So this will actually print out a sorted list of all of the grades for the class, right? And I didn't know when I was writing the awk program that it was going to be used for this. Sort didn't know it was going to be used to sort grades. But because we have the ability to pipe these things together, we have the ability to make these really cool programs do very generic things that can be changed depending on how they're composed with other programs. So what we see at the bottom is a number of processes that are strung together in that pipe. So we have cat into awk into sort. And if you look at the very bottom, we see in the kernel, each of them has a different file descriptor table. Again, these are just the tables that have a mapping of the different file descriptors to the actual resources, the kernel resources that they correspond to. File descriptor 0 is a standard input. File descriptor 1 is a standard output. So we can see that file descriptor 1 in cat points to the standard input of awk, and the standard output of awk at offset 1 points to offset 0 in sort. So we can see this is how pipes are implemented, that we're essentially stringing together a standard output from the previous program into the standard input in the next program. However, cat also calls open on grades.txt. So open creates a new file descriptor, which we see referred to as fd in the bottom, and that points off to a file. However, that's actually described within the kernel, right? So we can read from that file, and then when we write to file descriptor 1 in the program, it's actually writing to the pipe that takes what you're writing and shuffles it over to the standard input from awk. And awk, you can see, reads from file descriptor 0, which is the standard input, and it gets that input that was piped from cat. It does its own processing, and then it writes it to its standard output. Sort reads from its standard input, which, as we see, reads from the pipe that is written to by the standard output of awk, etc., etc., etc. And then finally, we get to the place where sort writes to its standard output, and because sort is not piped into something else, its standard output just gets written to the terminal. So this is really cool. Awk doesn't know that it's writing to a pipe. It could actually be writing to a file. Sort doesn't know that it's inputting from a pipe. It could be inputting from a file or from a networking socket, right? We don't know. So these programs are written generically. They polymorphically use these APIs, and the operating system, or specifically the shell in this case, is able to hook them together in an interesting way. Okay, so that's the big reason why we want to use file descriptors, not just paths that are passed into read and write. But there are other reasons. There are other really, really good reasons. One reason is if read and write were to take paths, we see on the left a interleaving of two different programs using the Filesystem API. So the blue program reads, and it's going to call read many, many times, but after it calls read once, but before it calls read again, the other process, the red process, unlinks, therefore removes the blah file. So the first read works, but then subsequent reads fail. This just makes it really hard to program. You need to consider failure in many, many different places all over the place. The logic behind it starts to get combinatorially really, really complicated. On the right, we see that this actually works. So we open the file called blah, and we get a file descriptor. We call read in our blue process, it works. We can unlink the file in the red process, but because the file is still open in the blue process, because we have the file descriptor to it, we can continue to read from the file until we're done with it, and then when we close it, then it may get rid of the file. Files are reference counted, both by references within the file system hierarchy and by open file descriptors. Only when all of the references to that file go away do we actually remove it. The file descriptor also allows us to have a data structure in the kernel that keeps track of the file offset, the current position within the file. How would we implement that otherwise, right? We'd almost need to pass that into each of these reads and write calls, and that would be horrible. And then this is maybe not so obvious, but it's a huge boon to efficiency. If we are using the path for every system call, then we need to walk through the entire file system path in memory and in the disk and check that we have permission to the actual file. So if you are accessing a file deep within the file system hierarchy, that's going to be very, very expensive. But if we open it once, then we have that expensive permission check. But after that point, we have a file descriptor open to the file, so we don't need that permission check anymore. So what do the data structures look like for a lot of lists? So I'm going to expand on this picture over the next multiple lectures, but it ends up looking something like lists. I'm sorry that normally we're used to seeing processes on top going to the kernel on bottom, but now the processes are on the left going to the kernel on the right. You can see that we have two processes, each with a file descriptor table, and we can see the top process is opening a new file called foo in the directory root. Right? So somehow this is going to need to be executed by walking through the data structures within the system. Right now, I'm going to assume that all of those data structures are in memory, but we will, over the next lectures, kind of disambiguate what happens when, it's actually on disk, because you have to get it from disk eventually. It is the non-volatile storage in the system. When it boots up, you need to read in all this data. So first thing is that a lot of Unix variants call the different entries that we think of as directories and files D entries. So I labeled that here. And you can right now just imagine that these have kind of linked lists that contain all of the D entries within directories. Of course, in the Linux kernel, where it's optimizing for this type of thing, there are hash tables and whatnot, but XV6 keeps it very simple. So when we make this open call within the first process, the operating system is going to say, okay, first I need to resolve that path, and then I need to create a file descriptor. To resolve the path, it needs to start at root, and then it needs to walk through home, then bin, then root. It finds root, and it's going to do a permission check. Are we allowed to execute that root directory, to actually open it up and see its contents? If we are, then it will iterate inside of it and then find the foo file. Once it finds the foo file, then it will create what's called a file structure. So this is called file in most Unix variants, and the file structure is what your file descriptor actually points to. So you can see that we've added to the file descriptor table a new pointer to the file structure that is at the offset in that logical file descriptor table of FD. So whenever we do an operation on FD, we're simply looking up at FD in our file descriptor table, which is a logical array. We find our file structure, and that points directly to the actual file system object that we're looking at. So this is essentially how you implement this type of thing. If we have another process that opens up the same file, then we'll have something that looks comparably like this. We'll add an entry into its file descriptor table and have a separate file content, a separate file entry to that. So this is effectively how we have multiple namespaces, the path namespace and therefore the hierarchical directory namespace, and a file descriptor namespace in the system, how they interact, why they interact in the way that they do, and how we go about implementing this type of abstraction. So I think this is a really, really important lecture to internalize, because how you think about designing APIs and how you carefully control namespaces is something that almost every single one of you will be doing in your life and will be doing in the future. So thank you very much. Have a good one. Talk to you soon.